Okay, here is a real life interpretation of the problem. So the straw represents the water slide. So the water that's being poured in is the inflow rate. The water that's being poured out is the outflow rate. And as the water level rises, it's the change in height. And then as faster draining at higher water levels, that like equates to proportional drainage. Okay, so like the water. So there's like a tiny hole at the bottom there. Get this right. So you can see the water exiting. Whereas if it's just a little bit of water, the outflow is minimal. But more, it's obviously a lot more pressurized. So that was why faster draining at higher water levels equals proportional drainage. So at first, obviously the water level rises quickly because the inflow rate is larger than the outflow rate. As the water depth increases, the drainage becomes stronger as we saw it increase its pressure, since the drainage rate depends on the water depth itself. So that directly connects to the model when we represented the differential equation dV output over dt equals 0.5 h. So this means that the deeper the water becomes, the faster it drains. And the differential equation tells us how the system changes moment by moment, depending on inflow and outflow. And in calculus, instead of only looking at one snapshot at a time, we analyze how quantities continuously change. And just like what I explained, like it's different moment by moment, so they change continually. And this demonstration physically shows the balance between inflow and outflow that was modeled mathematically in the equations. And then in terms of equilibrium, if I poured water at exactly the same rate that it drained out, the water level would stop changing. That would be the equilibrium. In my actual calculations, equilibrium occurred when the water depth reached 3.6 meters. So at that point, the slide would become unsafe because the safe limit was only 1 meter, as we know. But ultimately, this demonstration showed that calculus is more than just like equations on paper. It can be demonstrated in real life. And engineers use these exact ideas in models and real systems involving fluid, safety, designs, all that source in real world examples.